I've given a couple of talks online, but so that's good. I hope that everything goes. So when would you like me to?
So I'll tell you after 45 minutes, and you'll have still 15 minutes to.
Actually, there is a part at the end that depends on. I don't really know how the time will be, so I.
Sure. And also, I mean, since it's a focus soft matter dynamics audience, maybe you can, if we have some questions, we can ask also in the middle, I guess.
Yeah, for me it's okay.
Yeah.
For me it's all.
Already 36.
So that depends more on you if you prefer the dynamics of the questions at the end because of it depends on you. Because they are easy maybe to cut or to for the dynamics of the talk it's always better that people ask, of course, as much as they want. And I will answer as much as I can.
Yes, I mean we'll see. We'll try to take some questions, but then
No, questions are always
better. Else, yeah, if you lose the.
Sometimes you have a nice direct answer, or sometimes there is not. It's all good.
I think we are already 2 minutes past 5:30, so I'll just start with an introduction. So it is my pleasure to welcome Marisol Ripoll to give today's talk on hydrodynamic interactions. Many of them who are here present here have worked in the Ulish group. We have learned, Raghu, I have, and maybe Sunil and many others have learned directly these methods of hydrodynamic interactions, MPCD, directly from Marisol. So we know each other since 2007, and it has always,
yes.
yeah, it has been always been a pleasure to learn from her while we were there, and even beyond that, we have had many visits. Many students who, I mean, who were students and postdocs in the Ulish group, who are now faculty in various positions in India. I know at least Raghu, Anil, Sunil Pratap Singh, Anil, yeah, and so, Shiba most probably. Yeah, I see Shiba also, Shibananda Das. I think, and Marisol has worked on a large number of problems, and you can I can already see pictures of star polymers, which I took were from her, active pneumatic colloids, hydrodynamic interactions, active matter, and various things. Rather than give a very long introduction, I mean, because I can go on because we have a long history of interaction. I think I'll let Marisol talk about her work, and I hand it over to you, Marisol.
Okay.
Thank
Thank
you
you very much, Apratim. It's I want to say that it's a pleasure to be invited to this talk of ICER in ICER Pune, and well, I have besides all the long experience of people that have come to visit us that are now in India, I have also new collaborations, and it's I enjoy very much the collaboration always with India and with all of you, and I hope that the talk of today it's informative at different levels of your career. And well, I will say that the outline of my talk is essentially in this first transparency. I hope you see my pointer because I will introduce you first to the Forschungszentrum, where we are, and then what is soft matter, what is active matter, and what are hydrodynamic interactions. And in the end, I will also go through the main topic that you see on the title, which is if hydrodynamics are relevant in soft matter and active systems. So if you have any questions, please just don't hesitate to ask during the talk or to keep them for the end. So, whoop. Yeah. So the Forschungszentrum, I wanted to tell you where it was because some of you might, so we are in Germany, you see here on the left. We are somehow type of quite central in Europe. Although it's quite long that I'm settled in Germany, in Jülich, I come here.
Your slide has not changed. Have you changed your slide?
Okay, I don't understand because I'm seeing the new slide.
Raghu, are you seeing the new slide?
No, I am in the title slide.
In the title.
Yeah.
Okay. Now you see the whole talk again?
Yes,
I do,
yes.
yeah.
Let's see now. Is it better now?
Go to the next slide.
No, I am in the next slide. So
No.
now this is so you are only seeing the first one.
Yeah, now I see the next slide.
Yeah, but that you see the small, huh?
Yeah.
Let me, what should I do? Let me for a second stop sharing and sharing again. I will do the following. I will share everything. What do you see now? Do you see now my screen?
Yes, but again.
And now do you see the second transparency?
Yes.
Yeah.
Good.
Yeah, now it is
Oh,
fine. Yeah.
perfect. Thank you. Sorry for this. Okay, I was talking about that we were in Europe and that I was so that this is Germany and I come originally from Spain, which is a little bit south. And if you want to know where Jülich is here in this red spot, very close to the Netherlands, Belgium, and also France. So Jülich is relatively small, but close to all these very big cities. Oh, I cannot change the slide. I'm sorry. Now it's better? I'm
No,
sorry about this.
no problem. You have reduced the slide, I guess.
Yeah,
Continue.
the slide will be bigger.
Yes.
It looks like it will have to be like this.
Okay.
Yeah, but this will not let me animate.
But why is
I
this
have no
happening?
clue why. This is typically working. Now you see?
Yeah, everything is working. Now slides are changing. Yeah.
Okay, perfect. So this is a view of the Forschungszentrum. Will be quick. So it is almost 70 years old. Not yet. And it's not a university, it's a research center like ICER. And it's quite large. It's actually the largest research center in Germany. And I think it's the second in, so in Europe, we have CERN that it's bigger. And yeah, that it's here in the fields. And this is how it looks if you walk inside. This is a picture on the woods that I was biking this week. And this is our welcome into the Forschungszentrum. So, and now I come into introducing you to what soft matter is, which is, of course, a very large topic. And what does distinguish soft matter from liquid matter, or so from liquids or solid matter is 4 ideas I want to give. The first one is that the particles that allow us to understand what is happening in the system. So, of course, the matter is always made out of atoms and out of some atomic particles. But if you want to understand the behavior of these soft matter systems, you are typically focused on what we call mesoscopic particles, which are much larger than atoms. So our fundamental particles are much bigger than atoms, are micrometer-sized particles, but much smaller than any particle that you have to, that it's visible. When we think about billiard balls and something like this, our atoms, our fundamental particles are micrometers. You cannot see them typically. Since they are so small, they are very small, but they're in contact with even smaller atomic particles, typically water. And the interaction with these particles makes that thermal fluctuations are very important. And this is what brings this wiggling motion that you know as Brownian motion. So thermal fluctuations need to be considered always when trying to understand soft matter. And that is what allows us to understand why it's called soft. Since these thermal fluctuations are important, means that whatever structure is made, if it's ordered or unordered, it's possible always to be modified by thermal mechanical stresses, which are not very strong. They are of the order of thermal fluctuations. That's why it's called soft. And finally, another idea that it's important to bring is that we are used to a world in which inertia is dominating. You let something move, you push something, and this continue moving for some time. But in this micrometer size wall, viscous forces are dominating and inertia is not typically playing a role, which is sometimes going against intuition. But so you will see now some examples of this. So the first type of particle that you can understand typically like a soft matter system, the simplest is just the so-called colloids, which are small and without a very particular shape particles. And these colloids are everywhere in many of the systems that you have every day around you. For example, milk. Milk is made out of these, all these particles that you can see on the microscope. And the other type of structure, now I have problems with the transparency again. Sorry. Okay, are polymers. So once that you have a few of these colloids connected somehow, typically they are chemical bonds or many chemical structures, but we can think about them like if they would be springs, then the properties of the system change. They are long, flexible chain like macromolecules that behave differently in when they are in solution. And there are many examples around you. You have your soaps and many of these things. And for example, here I like the egg. The egg has this viscous structure that you know. And it's very interesting, for example, that when you boil, you go from a soft egg to a boiled egg, but you can never do the reverse procedure. And that's one of the, this is coagulation is one of the properties of these gel-like polymer structures. Then we have membranes, is another of the families of soft matter systems, that it's when you have many of these polymers or colloids connected into a two-dimensional system. And there are, of course, another big family of systems that have large biological relevance. For example, so all the membrane tissues and your skin and all of these are nice examples of membrane systems. And another family that we can identify is interfaces, which would be if you have two media, which can be two different liquids or two different polymeric systems, then there are particles that like to place exactly at the interface. And depending on how this is done, then the system has many, many different properties. You have foams, you have these coffee stains, and you have different systems. So, and now the next, so this was a very fast overview. And now I also wanted to talk today about active matter. But what do we mean by active matter? Is if you think about a system made of different components, typically you think about them like non-moving particles, but there are many examples in nature. And here I have a collection of nice movies in which you can think about these systems in which each particle, for one or another reason, has this self-propelled motion. So here there are these school of fish or these birds flock that are very attractive. In the large, these systems are big, but if you go to our microscopic scale, there are many bacterial systems or also synthetic systems like this. Well, this is a ratchet being moved by bacteria, but you can have other synthetic colloids that make this self-propulsion system. And here you have to think again about the difference between the microscopic system and our mesoscopic system, in which viscosity and thermal fluctuations make a difference. And well, I will not be able to explain all these systems here. I wanted to say something about length scales of active matter. There are many biological examples, as you see here, and many synthetic examples. So we humans moving could be example of active matter, insects, and then bacteria. And then inside the cells, you have all these molecular motors that also provide these propulsion and these active properties to the system. And in the synthetic world, there are many things, many systems which are man-made, that are also displaying interesting properties in soft matter system. We will be in soft matter active in this range from the around the micrometer scale systems. And then we arrive to the third piece of the title that I had not introduced, that it's maybe the main topic of today, which is hydrodynamic interactions. Which are hydrodynamic interactions? Many, as you have seen, of this soft and biological matter system exist in the presence of a solvent. This solvent is typically water. This is a picture that I found of seawater. And of course, what happens when you are, what is the effect of this solvent? Or are we able to understand the properties of our system just by the constituent? If you do experiments, then your system will have an effect or not, and you are not able to distinguish what they are. So I am a theoretician, and we can tackle this problem in different ways. So a first theoretical approach would be to ignore the colloid, to ignore the effect of the solvent, and to think that the main properties of your system come only due to the properties of your colloids, polymers, or whatever system you have. I have to say that this works in many cases. There are many systems that just by trying to understand the collision and this excluded volume interaction between particles, you are able to explain the properties of the system. But of course, this doesn't happen always. So the second level of trying to understand the system is to consider a random solvent in which we include these thermal fluctuations and these viscous forces that we were talking about, but without anything else. So it is just like each of the particles interact with the others and with some type of thermal fluctuations and viscosity. And that again is successful in a number of systems, but that we are here because some of these systems, this is not enough. So you need to know how by perturbing the properties of one particle, this affects the surrounding solvent that you can hear, that you can see here represented with these lines. And this affects how the neighboring colloids or polymers are behaving. So the definition, a very simple and intuitive definition of hydrodynamic interactions, is that they are solvent-mediated interparticle interactions. So it is not interactions that you have directly particle to particle, but it's due to the presence of this in-between solvent. Okay, I hope this is clear. And then the question is, how are these hydrodynamic interactions? Can I just give a general formula to them? And the problem is that they are very much system dependent. So it is not the same if you have only one particle that it's perturbed around the fluid, or if you have two, or what are the conditions around if you have whatever type of particles, what are the interactions of the solvent with your particles. So there are, for those of you that know a little bit about active particles, there are many examples of pushers and pullers, which are these swimming bacteria, these active bacteria. And if they are propelled through the bag or through the foam, the whole flow of the particles is different. So here you can see how solvent particles here like to arrive and displace down, while here they would do completely the opposite thing. So here the flow type of helps, and here it will go to the side. And this gives, due to hydrodynamics, a completely different properties to these two types of particles. Something else that's important to know is that hydrodynamic interactions are in general long range, which means that they are not trivial to include. So you cannot include them like a short range potential that it's easier to tackle, but in many cases you need to arrive to smart ways of dealing with these very long range interactions. They might be neglectable when they are not so long range, or when there are many other particles that they are interacting with, because then they type of cancel each other, and we say then that they are screened. But the truth is that in many soft matter systems, especially out of equilibrium, the effect of hydrodynamics is not really known. because experimentally you have them in, and if you do theory, typically you whether consider or not consider, assuming that they will be important or not. So how do we study this would be by comparison, and so there are different ways of studying this analytic by theory. Some family of solutions to study these are the analytical ones, which would be considering the full hydrodynamic equation in the continuum of the fluid, which would be through Navier-Stokes or through the Stokes equation. This, depending on the boundary condition, can become very involved. And then you have to see always which version of the equations are appropriate for your system. Another family of systems are the numerical approaches, simulations, and there are quite so many in the market. All of them have advantages and disadvantages. Stochastic dynamics, which is essentially molecular dynamics with Navier-Stokes, dissipative particle dynamics, lattice Boltzmann, and multiparticle collision dynamics. These are all very important and very powerful techniques. But today I will focus with the one I know better, that we have been working with in ULI for the last 2 decades, I would say, and that Pratim and several members of the audience are already familiar with. And this is multiparticle collision dynamics. It is not my intention today to give a very precise lecture of what, so it will be just this transparency and the next one. I just want to give you a very brief idea of what this method is. So it was introduced by Malevanets and Capral already, many? 25 years ago. That's long ago. And it has shown to be useful in many systems already. The idea is how to consider the solvent. And the solvent is considered by particles that don't have a size. They are point particles. They don't have excluded volume interactions between others, and they can have whatever position in space and whatever velocity. And the dynamics takes place in 2 steps, which is in the first step, they are just freely moving. Since they don't have a size, they are, you don't have to take care where the others are. You can just propagate them with whatever velocity they have for a finite amount of time, which is h, which is an important parameter. And then after this time, the particles are sorted into boxes, and somehow they interact momentum only with the particles that are in this box. It's important that momentum is conserved, and you have hydrodynamics. In some cases, I also like that they conserve kinetic energy, because then we can see what happens with temperature difference. But the most important idea is that they stream and they collide, and then the momentum is the same before and after the collision. So it sounds very simple, but you can, looking at the details of the system and doing all the proper analytical behavior, you can relate these really to systems with Navier-Stokes equation, and with all the cases that I know so far in which you can compare systems with and without hydrodynamics. I will show you 1 or 2. It works very well. You really have hydrodynamic interactions with this very easy idea. And then what I've said so far is only the solvent. What happens when you want to include properties of any soft matter systems like colloid, polymers, or membranes? Yeah.
In the previous slide, the momenta remains the same, meaning they can change their direction, but the magnitude remains the same.
Okay. Here, the idea is, I didn't want to go into this rule. Here, the idea is that each particle sees the velocity of the center of mass and rotates the relative velocity to the center of mass. That means that both the direction and the intensity is changing. So if you have one particle that is very fast interacting with other ones that are slower, the slower will become faster. It's not just a rotation, it's the rotation of the relative velocity. And this subtlety means that there is really a transfer of momentum between particles. It's not just the direction. Does that answer your question?
Sorry, I misunderstood. Okay, thank you.
Yeah. So it is, as I say, it is, I mean, to understand the method takes a little bit longer, but the idea is that it's a simple interaction, that it's very efficient to simulate, and that it really brings hydrodynamic interactions. But particles are changing direction and magnitude.
So at the collision time, there is no loss to momenta, right? There is no loss to momenta.
There is no
Marisol.
loss if you consider all the particles. So each particle is losing or gaining momentum, each particle.
But total,
the whole
nothing
box
is
not.
changing. Okay,
Yeah?
thank you.
So,
So
Sachin,
all the particles within
I
the
will
box
interject,
are...
Marisol. So,
Yeah?
because I know Sachin Jain, so I can guess what his confusion is. So, Sachin, here each square box that you see defines the velocity of the fluid, which is an average of the tiny smaller particles inside the box. So, it's basically see, a volume has a lot of gas particles, right? But the fluid
Yes.
velocity is the average of the velocity of the gas particles.
I see.
So what she is talking about is the collision between gas particles in a way that locally momentum is conserved, and locally within a square box you can define a fluid velocity. So the collisions that she is talking about are these small gas particles within a volume element. You
I see.
understand? So locally, always momentum is conserved, but the gas particles interchange momentum among themselves.
Right. Okay.
That's the picture. Yeah.
Yeah.
So it's a coarse graining. Yeah.
I see.
Yeah.
Okay. Thank
So
you.
in a way, these particles are not really any solvent particle. They are like an average. But the thing is that it's conserved within the box. And yeah?
Thank you.
Okay. You're welcome. And the idea is that then you need that your particle, so this is what I wanted to say here, hydrodynamics are not really imposed, but come out of this interaction with the solvent. And that comes for solvent with solvent, but also when you make an interaction with the solvent. And here again, I was not my intention today to go into the details of the method, but there are different ways of that your polymer or colloid can see the solvent. But always you use a technique that allows these hydrodynamic interactions to emerge. And you are not saying to the solvent if they have to be long range or short range or anything like that. It just comes out of this way of interchanging momentum. And in order to evaluate, which was the topic of today, the importance of hydrodynamic interactions is very useful to compare with a system that has no hydrodynamic interactions. And this can be done in different ways. One method that has been used for some time is this random MPC, in which the idea is that you have the same polymer dynamics with a type of an effective solvent in which there is no communication. Because here, if you interact one part, this solvent is interacting here with this one, and then there is transfer of information from one part of the polymer to another one. And that is what brings the hydrodynamic interactions. And here, if you say these type of sources are disconnected to each other, then you are breaking the information that goes from one part to another one, and you have no hydrodynamic interactions. And then if you have these two methods that are equivalent, and you say, I repeat my simulation that are almost the same, but with and without hydrodynamics, then you have a way of evaluating the importance of hydrodynamic interactions in systems where this is not known. But first, we are going to evaluate it in a system which is known, which is for flexible polymer dynamics. So if you have, this is known by...
So just one more quick clarification. I'm very sorry to interrupt.
Yeah.
In the previous slide, as you said, that the long range interaction emerges in your picture. Do you also know what would be the length scale in that? Do you have an estimate, or in a particular system, you would know that would be system dependent, that, what would be the typical length scale of the interaction?
That is system dependent. I'm sorry, I cannot go back to the, I don't know why here. I was, okay. I'm in the previous transparency now. It is system dependent. And I will show you 2 systems or 3 systems, and in each system, each new system that we study, we really try to see how it goes. Because sometimes you have to take care of it depends on, I mean, there are systems, if it goes with 1/r, for example, the interactions, and they are really long range, then you will have an effect always of the system size. If they go with 1/r squared, then you can, so you always have to take care of what is the effect of the range of the interaction.
Okay,
but
thank you.
In a way, you are not imposing it, you get it out of the system, because the surface conditions or whatever, they will be like that. But let me see if later I'm able to explain that you are able to see an example in which that's better seen. And the first one is very simple, very, as I was saying, is just flexible polymer dynamics. And you know from textbook that if you study a model, this Gaussian chain of connected bits, this is the so-called Rose model, and this is a polymer. If you want to understand the dynamics, you can do it with Brownian pure dynamic, Brownian motion, and then you arrive to an expression that says that diffusion coefficient should depend with the radius of gyration of how large the polymer is, with the inverse of the square. So it's 1 divided by the radius of gyration square. But this was known that experiments show this 1 divided by the radius of gyration. So here is where the first time was clear that something was missing in this Brownian description. And then Sim came with an idea of how to implement not Brownian motion, but a Stokes solvent. And the theory here was already predicting that the diffusion coefficient, so this is the center of mass of the diffusion of the polymer, should go like 1/rg. So this was known already through an analytical approach, and this is something that we tested with our multiparticle collision dynamics to see how it was performing. And here we have a polymer. So this is the diffusion. This is 20 years ago. The diffusion coefficient of a polymer with the radius of gyration with our MPC solvent. So here we were not imposing anything else than what I've just said. So we had polymers of different lengths and measured the diffusion coefficient. And what we were obtaining here was a beautiful dependence with 1/rg, which is not big news because it's what you expect, but this is more, so this is what was known from the theory, but it says that a polymer simulated with MPC really reproduced the hydrodynamic behavior and not what it's expected just by Brownian motion. I didn't say that the rotation here is slightly, here that the rotation has a slightly different, so the angle that you make the rotation is different, which brings thermal fluctuations into the system as well. So if you repeat the same system twice, it's not going to be exactly the same. It will be the same only in average. And so we have these hydrodynamic interactions with thermal noise and everything. And here we can check. So this is one of the first checks that hydrodynamics are nicely reproduced when you use polymer dynamics. And once that we knew this in equilibrium, this was my postdoc when I arrived in Jülich. The idea was to see what was happening in shear flow. And here we studied, so with Roland Winkler and Gerhard Gomper, the idea was to study polymers in shear flow and to do it with and without hydrodynamics. So if you have a star polymer, is that you have this long chain of colloids that are attached, and you can attach different of them through center of the polymer. And depending on how many of them you attach, you can do 2, then you have a linear polymer, 5, 10, 50, or 100. Then you get something like a very soft colloid with many arms that are waggling. But if you apply shear, which is that that the flow would go faster, would go in one direction to the right, in another direction to the left. So then the polymer itself is feeling a different velocity, is being dragged towards the right in one case and towards the left in another one. And that depending on the intensity of the shear, which makes is that the arms are aligning, that the whole structure is aligning. And then it would pass from a sphere type of a structure to something much more elongated. So increase in shear was inducing anisotropy. It was also aligning with this different flow that we were imposing. And furthermore, each of these arms was rotating. So you have that an arm is here and is being pushed to the right, then slowly the other arms are coming and pushing it down. I lost the movie from this, but and then each arm would come slowly down, would come slowly down and be pushed to the back. So if you follow, each of these arms is performing a rotation. And this we did at the very beginning with our MPC method, and we were very happy of seeing the results and how this was happening, because we could also compare it to experiments. But then the question came, what is really the effect of hydrodynamic interactions? Then it was the first time that we did this with and without hydrodynamics. And here what you see is a summary of the results in which you study the angular velocity, so how fast these arms are rotating, and divide it by the shear flow. Of course, the larger is this difference of velocities, the faster is rotating. And what you see is that when it's spherical, this is linear, so this would be this line, but slowly you are not applying, you don't have an spherical object, and it's a little bit, it gets elongated and it rotates a little bit slower. And what you see is that in the presence of hydrodynamic interactions, this is the blue data plus hydrodynamic interactions, at some point it doesn't increase anymore. So this goes like 1 over the shear. I didn't say this is the rotational velocity, and this is the shear. So this Weissenberg number is the shear with a characteristic time. And you see that this scales very well, and that that doesn't depend on the shear. While if you don't include hydrodynamic interactions, this decrease is also slower, but it continues increasing. So here there is a significant difference, a measurable difference, in what is the difference in including and not including hydrodynamic interactions. So with no hydrodynamic interactions, keep increasing. And this is the first thing we could measure that was not known, that it's really an influence of hydrodynamic interactions. The reason is that when you have, so if you have our method that has the solvent plus the star, you can also study what happens with the solvent. And then you can see that not only the star is rotating, but also the flow is being dragged with it. Okay, so, and that's the reason that makes that there is no further increase, because it cannot further push both things. And then I'm talking too much.
Can I ask
because I wanted. Sorry?
Can I ask a question? The previous slide.
Yeah.
So in the with hydrodynamics and without hydrodynamics, the coupling scheme is same, or the solvent and
yes, it's this type of, these are details, but this type, we always try to make it as similar as possible. So here it is not the same, because here you see the real solvent particles and here not, but in a way the friction and the diffusion coefficient and all these numbers that characterize the solvent are the same with and without hydrodynamics. That's the idea. That's why I mean, there are not many examples in which we can precisely compare, but that is what I want to bring today. And I see that time is running. Okay, let me say something about the, because I think some of you in the audience knew about the star polymers. Pratima is actually an expert. And I wanted to say something about this flexible helix. So we did something similar with a rigid structure. So some years later, and where we were applying the shear, so instead of a flexible polymer, to a rigid helix. And then you see this type of tumbling that I was talking about. And you can follow, if you follow one of the peaks, then you see how it comes up and down. Here we were interested in the effect of flexibility. And if it's semi-flexible, you see that the flow deforms a little bit the helix, which can come back. And then we can characterize the structure. So here, the point is that we do this also with and without hydrodynamics and looks almost the same. So this behavior that you have of the rotating helix does not need hydrodynamics to be characterized. And,
Marisol,
but yeah.
I have a question. Even before the helix, you would try with a pneumatic rod, a rod like. So you started with a helix. Is the result with just a rod? You are using a rigid helix, but you could also just use a rigid rod. Is that result known or trivial or something?
Yeah. There are many. I mean, there is. I mean, this is a summary of 1 hour.
Okay.
In principle, if you have a rod, you get the same. I mean,
Okay.
it is. So the point is. So what I want to convey in the whole talk is that hydrodynamics are subtle.
Okay.
Sometimes they
Okay.
have a very strong effect, and sometimes they don't. So
see.
you cannot say a priori when to neglect them or not. If I would show you here just a rod, there would not be any difference with or without hydrodynamics. So this is just a Jeffrey orbit.
Okay. Okay.
You see what I mean? So you are right. I could have done this with a rod, but the helix is more interesting for what I'm going to say now.
Okay.
If you have a helix, there is something so-called vorticity displacement, which is different from this rotation, is that in the angle. So, let me see here. Sorry. Oh, I didn't put here the 3 axes of but you have the direction. I'm sorry for that, but you have the direction here in which the flow is going. This is the flow direction. In this direction, the velocity is changing, is what you call gradient. And then there is the direction for the younger students that goes towards the plane. And that's called the vorticity direction, in which in principle nothing happens. So in most cases, in the vorticity direction, nothing is happening because you don't have the flow and you don't have the gradient. And here, what it's seen in helices is this vorticity drift, is that the helix is displacing along this neutral direction. And if we make simulations with our hydrodynamic method, we see that this is the displacement in this neutral vorticity drift. Okay, and then you see how this vorticity drift changes with time for a particular intensity of this shear. If you change the shear, of course, if it's weaker, this vorticity displacement will be smaller. And if here, interestingly, it doesn't matter how strong you put the shear. If you put no hydrodynamics, there is absolutely no vorticity displacement. So this is another example that I have chosen from the systems I've been working with, in which hydrodynamics are relevant. Because if you want to say, I'm just interested in how my rod or my helix is tumbling, then you don't need hydrodynamics. Just the shear would be enough. But if you want to see the full thing that it's happening, that it's also displacing in this vorticity direction, then you need a system in which hydrodynamics are included.
So Marisol,
here,
sorry to interrupt. Does it depend on the rigidity of the helix, or is it same irrespective of how flexible or how rigid the helix is? What is it?
This is an effect that depends on chirality.
Okay.
And if the helix is flexible, the chirality reduces. So if you look here, and you need that the structure is chiral. And this is more chiral than this one. Because here, but this one down, although it's flexible, it still keeps this right-handed and left-handed. So the effect will be a little bit smaller, but will still be there. If you think about a completely flexible polymer, then the chirality is gone, and then the vorticity displacement also.
Okay, thank you.
And
Yeah.
So that, and I had here an explanation of why this happens, but time is running, and I think I wanted to tell you. So if you are interested, I could tell you in another moment. But it's really due to this chirality and to the fact that that you have left and right-handed things. But let me tell you something about the self-phoretic swimmers that start in them from the very beginning. an explanation, a quick explanation of phoresis. I think I am sorry, but I had too much material. It's so if you have, we have seen if we have a colloid with solvent particle around, there are all these kicks that are what you know all as Brownian dynamics, as Brownian motion. And here, these kicks are very strong, but they're the same in all directions, such that there is no displacement on average. But if you have a system which can be the presence of a temperature gradient or the presence of a chemical gradient, if you have a system in which the interactions are not the same, if there is a gradient, it's not the same left and right, then these strong interactions are not compensating and you get a net displacement. And this is what I call phoresis. So just for the fact of having a particle and a solvent, and that this solvent is not homogeneous, will mean that my particle likes to go to one of the two sizes. In the case of a temperature gradient, it could be going to the cold here or to the warm. Okay, and yeah, and with this, so something else that it's is that the typical gradients in the microscale, because you have gradients maybe of 1 degree or 0.1 degrees on a particle that it's 1 micrometer, means that the gradients indeed are huge, because this is 10 to the 5 Kelvin per meter, so in our scale everyday life, and that makes an effect that these particles are really displacing. And here I wanted to show you some experiments, but it's and here at the very beginning we were just to show you that we had these type of interactions that we can reproduce this effect. Here I need a surface also with MPC. I need a strong interaction on the surface of my particle. But then we have particles, if you have attractive interactions, there are details of the simulations you can change such that the particle likes to go to the cold or to the... And what is very important is that not only the particle likes to go to the cold or to the warm, but also the whole flow field around the particle is being introduced, which means, talking about hydrodynamic interactions, that these hydrodynamic interactions are going to be very important in this type of systems. And that's what I wanted to bring, because these phoretic particles were not so well studied. And that's a crucial ingredient to understand their behavior.
Could you,
yeah?
You said that you can change the surface to make them go towards cold or hot.
Yes.
Is it possible to say how is that possible briefly, or it can wait till
you
the
mean
end?
In experiments or in simulations? So in experiments,
I mean, I don't know. I mean, what is the principle that a particle will sometimes move to hot or sometimes move to cold?
well, there are books about that. And there are many in the world of thermophoresis. There are many explanations here. This I was jumping too fast, but here, these are experiments. These are experiments in which they, if you look at the pink line,
yeah.
These are experiments of a particle of a particular size, 0.2 microns. And if they have the same, and here they're measuring ST is the...
Sorry, coefficient.
Eh?
Sorry, coefficient.
The Sorey coefficient that measures the force that is bringing to one or another direction, let's say. It's a force that is proportional to the temperature gradient, has here typically a minus sign, and this means traditionally was in units of temperature. I like more this dimensionless number. But in principle, if this Sorey coefficient is positive, it means that it goes to the cold, because they are measuring a force that goes towards the cold. And if it's negative, it goes to the warm. Okay, because you are measuring the direction of this force. So this is giving us a direction. And here they see if the average temperature is 5 degrees with the same gradient, this particle will like to go to the hot, to the warm. And if the average temperature is 30, then it goes to the hot. Why that happens? Because the interactions of the solvent particles, so there is a certain chemistry of this colloid, and how does it interact with the solvent and how this thermal, it's not really known. why, what is it changing around the particle that makes that the interactions, which are temperature dependent, are different at different average temperature. But this is an experimental, well-established result, and they observe this. In our system, in the case of simulations, I can tell you, because I need the interactions around the colloid to be strong enough. And then what we have to do is to have, so we have molecular dynamic interactions between the surface and the solvent. So I have my MPC with molecular dynamics, and then of course I can have them like attractive, very close to the surface, or completely repulsive, which is a Lennard-Jones or a WCE. Okay, and if it's Lennard-Jones, then it likes the cold, and if it's completely repulsive, it likes the warm.
Okay.
And I have explanations, but it's type of very, you know what I mean? But this is the way. So here I'm really changing the type of interactions, how the surface of the colloid is seeing the solvent. And that is what makes the difference. And in experiments, they are also changing that, because there will be more attractive, or but exactly in each case is not.
Okay.
But that's, yeah.
Okay,
And
so you can focus on the hydrodynamics maybe. I got the.
Okay.
Yeah. Sorry.
The point is that one talk always triggers many other questions. That is nice. But okay, also the fact that you have these going to the cold or going to the warm, or the type of interactions, also changes how the solvent is reacting to this. And here you have just one example. And again, I will go very fast here. We can solve again the same as we were doing with the polymer equilibrium. This is a case in which we can solve this from the Stokes equations, and we can see what we expect from the hydrodynamics. So we don't know if our simulation is doing it properly or not, but we can compare. And to make a long story short, just look at the blue line, which is what considers all the proper interactions. The blue line is what you expect from the theory, what you expect from hydrodynamic interactions, because in this particular case can be measured, and the dots are what we are measuring in experiments, in the simulations of MPC.
Marisol, sorry to interrupt. So are these porodic colloids always neutral swimmers? Like from your flow field here,
This
I can see.
porodic colloid, which I'm showing here, is not a swimmer. It's just a colloid in a gradient.
Okay. So it creates this flow field around it. That's what you're saying.
Sorry, it's just going around. And here I want to say that I have an wait a second, but it's coming in the next transparency, I think. Here I want to say that I have the proper hydrodynamic interactions, or to the extent that I can measure. Here I can check that it's correct, and that was. And then here is where the swimmers come. Then what happens if I, instead of having a particle in a temperature gradient, I attach the source heat to the particle? If I attach this yellow now, is the source heat, and I put my colloidal particle, then I am feeling this particle is always feeling the phoresis. And then it likes to, because here I know how to have a particle that likes the worm, and then this particle likes to go towards the worm. So I will have a particle that swims in this direction. Okay, but here, if you put close another particle, this guy here will go towards the hot, and then will go towards the hot of its own particle, but also if there is a neighbor, which means that you are inducing not only motion, but also attraction to the neighbors. Yeah, and the similar idea if you have a particle that it's thermophobic or anti-chemotactic. So if the whole same reasoning can be done with, not with temperature gradients, but with chemical gradients. And then you have the same, if they like chemical rich or chemical poor, then it will go in opposite directions. But here you can induce attraction or you can induce repulsion. And this has been, I wanted to show you, these are the self-propelled particles. These particles have been synthesized in the lab. We like these dimers, and they are doing this Janus type of particles. And they are also examples of Janus type of particles in catalysis. And how are the hydrodynamic flow fields in the case of these swimmers and in the case of these dimers? They are quite intricate. So they are quite So here you have one of these dimers in which the two particles have the same size, or one of the exactly the same, but that the heat is a little bit smaller. You would think that this effect is not so large, but you see the flow fields. Here you change, you have to see these fields like if you are another particle swimming here. If you're a particle swimming wherever, you will be dragged along these lines. So this is how the flow is bringing you. And here, the flow will bring you towards the dimer, while if you reduce this size, it's bringing you far away. So here you have lateral attraction, which is pusher type, and here you have lateral repulsion, which is puller type of flow. And with this is not so easy to know in advance. And this is also not really, so this is different also in near field and in far field. And it's not exactly what you expect of a standard pusher and a standard puller. So this hydrodynamic, it is, yeah, just different. And which, how are we with the time? So we make, in order to make this proper, I want to be honest, we need these pretty large structures. So this is more to scale the amount of solvent that we have to have hydrodynamic interactions. And then we see simulations that are going to look like this. So we need this high performance computing. And in order to compare again now, in the case of without hydrodynamics, I will not have time, but you can make a model that was developed with Sergi, that now we have also for the case of chemical gradients, which I've not cited, unfortunately. But okay, here I don't have time to explain you the details, but please believe me that here we have everything, all this phoretic attraction and repulsion that I was talking about here, but no, so this attraction and this motion, but without the hydrodynamic interactions. So we can make the same simulation with all the ingredients of phoresis, with hydrodynamics, and with all the ingredients of phoresis, but without hydrodynamics. And that is the movie that I'm going to show you here. So this is a movie done with hydrodynamics, and this is a movie done without hydrodynamics. This with hydrodynamics needs the supercomputer. It's very expensive. The formulas were a little bit complicated, but it runs very quickly because it's just an interaction, an effective interaction between particles. And what you see in a first view is type of similar, because we have attraction between these particles and they try to make this agglomerate. And here there is also attraction and they are propelling towards the head and they also make these agglomerates. But if you look carefully, these agglomerates are type of different, because here you have, for example, this particle will swim away. So, and it's keeping attached here due to the influence of the flow, that it's dragging it to the rest of the cluster. While here, all the cluster is being formed with the colloids facing into the cluster, because what it's driving this cohesion, this clustering, is really just the phoresis, is just this thermal attraction, not what it's being brought by hydrodynamics. And well, here I wanted to explain this better. And you see this, how these clusters are being formed, the dynamics in a very early stage. You also see that here, for example, particles like to swim with the flow, because here you have this interaction in the back, and another colloid here, what you see, likes to swim behind it. While if you have no hydrodynamic interactions, they swim together, but they swim because they are feeling simply the heat of each other. They swim and they propel together. And how are we with time, Pratim? Hello?
Hello, we are covering 1 hour, but I think we are, at least I am interested to listen to one more. So we'll continue for 10 more minutes. So if people are tired, they can drop out. This is in 2D, right? Or is it in 3D?
This is quasi 2D.
Quasi 2D. Quasi
this
2D means
yeah,
please go on.
I'm running too much. Sorry. This is. So this means that this is quasi 2D confinement. It means that we have like walls in which the fluid is confined between these two parallel walls, and the particles are swimming in this. So the hydrodynamics is 3D, but the colloids are not able to move up and down. So you see, it's like if it would be sedimented on a surface.
Okay, sedimented. So there are two walls. They are confined by two explicit walls, where MPCD would do a bounce back. The MPCD particles will do a bounce back.
The solvent does that, and the colloids are just fixed in these. Yeah.
Do you always? I have a question.
Yeah.
Do you always need these boundaries?
What do you mean by boundaries?
Systems? The walls.
What do you mean by boundaries? So if you have the fluid here confined between the walls, you need that the fluid doesn't escape. Is that what you mean? And something else is what does the fluid?
Yeah, go on, sorry.
Yeah, and then another thing is what will happen here on the border, and there we have had a periodic boundary condition simply.
Yeah, maybe I can ask this question later. Yeah, we can go ahead.
Yeah.
So, but I mean, we actually have also simulations with 3D. But then the dynamics, so I can also show you that, but it's more difficult to see the effect. So in 2D is like more, in this quasi 2D, I find, especially for the importance of the main message that we wanted to bring today is if hydrodynamics are important or not, which you see is what I'm trying to come back all the time. This was much easier to see. Okay.
Yeah. I have also questions about boundaries, but I'll wait till the end of the talk. Yeah. But there was some other question, quick. Yeah.
Okay. Okay, but you have seen a few effects here of this system that come due to the presence of hydrodynamics. So the way that they are linked together, or the way that they are, and the type of structures they form afterwards. Oh, sorry. Here. It really comes out of you cannot see this type of systems with the tips out and how they are, and some of them, we call this backward sparking, because some of them arrive, see the system, and this hydrodynamic flow makes them rotate and attach to the system. I don't know if we will see one of them. So this one, for example, is really coming back and being attached, and that can never happen if there are no hydrodynamic interactions. So here the effect is completely, the type of dynamics of the system would not be possible without hydrodynamic interactions. And if you change the shape of the particles, we said that the hydrodynamic interaction, the hydrodynamic flow field around the particles was going to change. And indeed, what we see is something different. This is actually unpublished still. So here, you need these hydrodynamic flows, which enhance very much this type of coherence. It's what this extra attraction is making clusters that, with simply the phoretic attraction, are not clustering in the case of the absence. But this we know just because we are comparing both of them. And this is a summary also of many several unpublished results in which you see that, for example, in this case that I saw a little bit more in detail, you have structural changes. So you get clustering in both cases, but the structural changes are different if there are hydrodynamics or if not. In this case, you have that hydrodynamic interactions are really enhancing aggregation. So since you have hydrodynamic interactions, you get these clusters that are much smaller if there are no hydrodynamic interactions. Here is pretty brutal, I would say, because you get that it all collapses very strongly, while here they are only getting type of stacking small clusters. But this is the case, in this fourth case, we have a case in which So here you see that we have changed the shape of the swimmer. Instead of having one phoretic and one attractive, we have put two of them. And in this case, with the same, these two plus a particle in the back, which means that this is moving towards the head, you get that here hydrodynamics does the opposite. Here it doesn't let the system cluster, while if there are no hydrodynamics, the system can cluster. So here hydrodynamics makes a repulsion, here it's enhancing aggregation, and here is diminishing aggregation. And then we have this last example in which we had a hot particle together with a phobic and a philic particle. This was type of propelling in this direction. And in this case, it hardly makes a difference if there is hydrodynamics or not. So you see some effects, but they are really, really minimal. So you get that for this particular system, to include hydrodynamics or not would not have made the difference. But this, and with this I can conclude for today, you cannot say if the hydrodynamics are not trivial, like is the case of these phoretic swimmers, you cannot say a priori where are hydrodynamic relevant or not. You just have to try to understand in detail how the system is, and then make a conclusion if hydrodynamics are interesting or not. I was too optimistic when preparing this talk, and I had these Carroll systems, which maybe I can tell you another day about. But let me come to what I was saying.
You can just flash it in a minute or 2 minutes, so that we can ask the question after you finish. That what is the broad?
What would you like me to do? This is another 20 minutes, half an hour. I think it's.
A few slides on chiral systems.
Sorry?
A few slides on chiral systems.
You would like that. Okay, with motivation or without motivation? So let me see.
Without motivation.
Yeah, the motivation can come after I've thanked you, and then it can go on in the discussion.
Okay.
You can just flash the result.
I will tell you what we have done. I will tell you what we have done, and this system is. So I found I like these systems with solvent and rotation and activity, and I met Yongxian and Dirk, and they had these particles which are colloid-like particles, and you have to understand them because they have a tip that it's magnetic. And this magnetic moment is oriented perpendicular to the main axis of the rod. I hope this is clear to understand. And this, experimentally, what they do is that they put these particles in between cross magnets, and they apply a rotating magnetic field. And what happens to these particles is that in principle, they are preceding, they are rotating like a rod goes up and down, but there is a range of frequencies in which the particles stand up and rotate around their axis. I don't know if you are seeing me or if you see what I mean, but these particles stand up and rotate. And then we thought that this could be done with simulation, and Josh Ameke, that was an splendid PhD student, we thought, okay, these particles are rod-like, they have this tip and they're rotating, but in principle, once that they're rotating, they're just dragging the flow around it, and that is what makes the most important description in the system. And we, since the main dynamics happens in 2 dimensions, because that's what we are dragging, and we wanted to simulate many colloids, here we were simulating really just a 2D system. So we said we have disks that are interacting with a solvent through MPC, and they have interactions in the surface of the colloid, and they are just rotating. So these are the simulations we do. And then what happens if you have another colloid close to it? These are 2 of these rods that we are seeing from above, is you see that they are rotating around each other. And well, this is beautiful. And if we do the simulations, we see type of the same effect. So here we are not, each particle is just rotating, it's not translating, but due to that it feels the flow of the neighboring particle is being dragged around it, okay? And we can compare the rotation of these 2, how they are rotating depending on the distance, and we see a nice comparison with the theory, which is the black line, and experiments is always in red, and simulations in blue.
These are co-rotating ones.
This is just 2 of them.
Co-rotating.
Yes.
Rotating in the same direction. So same
We
chirality.
make them, yes, we make them all rotate in the same direction, and then it's the flow field that makes them rotate around each other. And here, of course, this would be almost impossible. So this is really due to the fact that there is a flow. If you just make one particle rotate, it would not influence the other. And it is not that we impose a rotation of one particle of the other one, it's that the flow is doing that. That's the message.
Oh.
You see what I mean? Okay.
Yeah, sure.
Thank you. And here, maybe you can see what happens if instead of 2, we have many of them. If you have low densities, you can see that there are some of them that perform Brownian motion because they don't see neighbors, but when they start to see neighbors, they start to perform these much larger trajectories and to start to form. And here, when you have many of them, here, these are a few trajectories that are being dragged, then you see that they are translating very far. So they don't do Brownian motion anymore, but since they are always close to another colloid, they perform these very large trajectories, and they form these eddies and these. And what this work has been about, here we measure the velocity. Let me show you this movie. So this is a very large simulation in which you see the red dots in the back are each of the rotors, and the black lines are just trajectories to emphasize this formation of vortices, which, well, I was happy with because it also looks very much like experiments. And then here we were able to measure these in order to prove, because so for the eye, this movie that you have seen looks very much like turbulence. I'm sorry that it goes like this. It looks like turbulence, but in order to say that this is turbulence, you have to check that the energy spectra is really covering all these possible length scales. And this, since we had the data over all the colloids at all lengths, we are able to compare here. All the blue data is simulated